Yeah. Okay. Well, let's get to it here in a second. So if memory serves, we were going to look at one thing from last time again. What was it that we were going to look at? I don't remember precisely the thing. Um, what was it? Oh, solving this. Yeah. Okay. Um, Actually, for sake of time, I'm gonna cheat here and actually show you guys one thing from um, that's kind of handy. Oops. Oh, and I can't switch the. Okay. Let's do. I'm gonna just use Wolfram Alpha for this. Okay. So, what was the fraction that we started with? Um, what was it, Will? The before we split it up. Either way. Uh-huh. Let's see, where's the x squared plus 1, parentheses, x minus 1. Okay. And then I need another set of parentheses, and then there, I need a left. Um, this is just it's basically Mathematica online. Um, but I've got Mathematica on my computer, but the way I've got the projector configured is I can't um, swap it over, and you guys can't see this on the. There we go. Why is that not capturing? Oh, that's right, because I'm on the Elgato. My bad. There we go. Okay. So here's a. You can do this with Wolfram Alpha. Mathematica also can do this too. I wrote the command in Mathematica syntax oops, um, because I'm used to it. But you can have um, you can have it manually or compute for you the partial fraction decomposition. And so here's what it turns out to be. Um, and so let me just sort of we'll copy that down, and then we'll look at this and say, okay, now what? How do we do the integral of all this stuff? Okay, so the format here, it put like there's the constants are 1/2, and it just puts the 2 in the bottom there. We'll rewrite that slightly when we do it back over on the iPad, but if we slave through all that algebra, eventually we would get these constants. Great. Um, this, by the way, can be a really handy tool to, after you do a partial fraction decomposition by hand, double check it against the machine just to make sure that you didn't make some arithmetic error. Because that honestly is where most of your errors are going to be with this, is with arithmetic or algebra. Okay, so um, um, yeah. Right, exactly. So all we did last time was we set up the form of the decomposition, but we still had A's, B's, and C's. And then we set up the equations for what the A's and the B's and the C's would like, how to figure out the ABC. So that was um, this, right? We said, okay, it's going to split up like that. And then if we go through and try and figure out what the constants would be, we would end up with this system of 3 equations and 3 variables. And that's right when we ran out of time. And so, like, this is solvable using high school techniques of either elimination or substitution or something. It would just take a minute. And for the sake of time, I'll just say, okay, machine, you do that part for me. And bam, we got whatever we got. Okay. So, what did we get, Will, for this? It was the machine's fine. Okay. So, I'm going to rewrite that slightly here as negative a half x over x squared plus 1 minus 1 over x squared plus 1 plus 1 half over x minus 1. Okay, same thing. I'm just going to kind of write it slightly different. And the reason that I chose to write it that way, well, a couple of reasons. First is I want to leave the denominators basically as clean as I can possibly get them. And that was the sort of form we had a minute ago. The other thing is that the first term that came out of the machine had two terms on the top, right? Negative x and minus 1. And I choose to break that into really two sub pieces, the x part over the x squared plus 1 and the constant part, and that should be a minus a half on, sorry, on top. This right here should be a half. Minus 1. I'm just messy. There we go. Yeah. My handwriting leaves something to be desired. Okay, good. So, uh, so that's what we got from the machine. Um, Slightly rewritten just for my sanity. Okay, wonderful. Now, what we want to do is, um, let's see, how do we integrate all of this? Well, the reason I split it into three pieces is because each piece will require a different technique. All right, so let me actually just rewrite. Let me copy paste this here. And then what we were interested in is, of course, that. And the three parts are going to require three different techniques of integration. Okay, and let's think about what techniques are we going to use? Let's actually start at the far right. What technique is that going to use? Yes? No? No idea? You just do it, it's a logarithm, right? So that's basically du over u. Yeah? No? Okay, sure. Okay, so this one just becomes 1/2 natural log of x minus 1, right? Okay, so that one's easy. What about the one in the middle? Again, you just do it, but which one is it this time? And if you say natural log, I'm going to come beat you with a stick. Not really. Morning farting. Uh huh. Okay, what's the integral of that? Help him out. Arctangent, yes. What? Yeah. Okay. So the one in the middle is just arctangent, and then of course we've got a minus a half out front because of the numerator. Okay, great. And then finally, what about the term on the far left? What do we need to use there? You are not. Okay. You can take the 1/2 out, sure, but you can't take the x out. Sorry. Okay, Jack. Yeah, it's a u substitution. Okay. So this one we'll go ahead and write out. Okay. U is x squared plus 1. Du is 2x dx. So dx is du over 2x. And so we have negative a half x times dx is what we said, du over 2x over x squared plus 1. The x's cancel, and so we'd end up with negative a quarter integral up, sorry, that should be a u in the bottom, du over u, which is negative a quarter natural log of that. And in this case, actually, because x squared plus 1 can never be a negative number, I don't need the absolute value, right? Because what's the smallest x squared plus 1 can ever be? 1, right? Because the smallest x squared could ever be is 0. Okay, great. Okay, so that gets us our three terms. So the reason I wanted to break it up like that was to illustrate a point here that when you do this, there are only ever 4 techniques of integration that you could possibly need to use once you've broken it all up. You're going to have terms that have logarithms. You're going to have terms where you have to do a u substitution. You're going to have terms that are basically arctangent, and terms where you might have to do a trig substitution of x equaling a tan theta. Okay, which that kind of includes the arctangent one in it. Okay, so the why is it only those 3 situations, or 4 if you count the trig ones as 2? Well, how did things factor? How do polynomials factor? Right? What was the fundamental theorem of algebra? If I allow myself to factor things and I don't use complex numbers, then every polynomial factors into a product of and right. Okay, so monomials are linear things, right? So x minus 1, x plus 7, right? Those are monomials. Irreducible quadratics are going to be something like x squared plus 7, or something where you cannot factor it without using imaginaries, okay? Well, the irreducible quadratic ones are either going to give you the things where you do a u substitution or a trig substitution. The linear terms are going to be the ones where you do a logarithm. Great, there we go. Right? It's going to break down to, right, each piece would be relatively easy once you get it broken into all those pieces. Okay, now, there is one minor problem um, about factoring polynomials. It's hard, okay? By which I mean it can actually be impossible. Okay, so this is actually one situation where polynomials and numbers are a little different. So it turns out that, well, let's take this. You guys all learned the quadratic formula back in high school, right? Or in middle school, hopefully, right? Maybe you even learned the song. Did anybody ever learn the cubic formula? Yeah? You've seen it. You certainly didn't learn it. And if there's a song attached to it, it's Anagata Davida. Okay, that goes on for 20 minutes. Okay, because if the quadratic formula takes up like a note card, the cubic formula would take up pretty much every chalkboard in this room. Okay, to write it all down. It's just horrible to write down the formula. Like, it's really terrible. Okay, maybe not every chalkboard in this room, but it would take a substantial amount of writing. Huh? Well, let's go to the bastion of all knowledge of Western civilization. Oh, well, if you have a quintic equation, or I mean a cubic equation, so like, oops, um, all right, let's go to Wikipedia, the bastion of all knowledge of Western civilization. Um, there, okay, and that's only a special kind of cubic that's called a depressed cubic, meaning that so if you don't have an x squared term, but you do have x cubed, x, and constants, we call those things depressed cubics. They're sad because they don't have square terms. Yeah. Okay. Anyway, so if that's the case, then that's one of the parts of the formula, right? So it's just really, really terrible to write all this stuff down. Uh, Nah, but that's only one of the three roots, right? Well, okay, so how many roots is a cubic have to have? Has to have precisely three. Again, fundamental theorem of algebra. But two of them could be imaginary, right? But also on the subject, how do imaginary roots come? If they are imaginary roots, they have to come in pairs, conjugate pairs, right? So if you have 2 plus I as a root, then you know for certain you have 2 minus I as a root. All right, well, if a cubic has 3 roots and the imaginary ones have to come in pairs, then what are you guaranteed that at least one of them is not imaginary, right? Okay, well, that's the formula for the one that's guaranteed to not be imaginary, and then the other two are a different matter. Once you crack that one, then the other two are easy to find because you can just do long division and then use the quadratic formula. But getting that first one, that's the hard egg to crack. Uh, okay, what about a quartic formula? Well, if we can solve quadratic, cubic, can we do degree 4 polynomials? Probably. Um, yeah, you can. No, it's not. Um, let's talk about that later. Okay, this one, right? Here's the formula, but of course the B's and A's and stuff are themselves like it's even worse, right? Okay. Now it is solvable, but it's horrible. So then you say, okay, great. What about a quintic formula? Guess what? There isn't one. We know we can prove that it is impossible to solve an arbitrary quintic equation. Now, you might get lucky and be able to solve this one or that one or some other one, but in general, there is no quintic formula, or and therefore no 6th degree, 7th degree, and so on. It is, and so the question was, is it worth asking why? I invite you to become a math major to learn that, to learn those answers. Um, yeah, it has to do with basically two equations and their roots. You can attach a mathematical object called a group, and this is a bunch of sort of 19th century mathematics where you say, okay, what can the structure of that group tell me about the equation that it was attached to? And then based on knowing things about the structure of groups, you can, yeah, I mean that's the elevator speech, but really it's become a math major to learn the secrets of the universe. Okay. Okay. So my point though, are we going to give you impossibly hard problems? Of course not. But in general, factoring polynomials is very difficult, if not impossible. Okay. Okay. So the last thing I wanted to say on um, the subject of integration by parts is what happens if you have something like the following. So what happens if you have repeated factors? Okay, this can happen. What does that mean for the form of the decomposition? Well, and I put squiggle on top because I don't really care what the numerator is. I just want to sort of think about how is this going to break up? Well, if you have repeated factors, what's a little annoying is that you have to do this. Okay, so in the first one, the first example here, I've got x minus 1 cubed as my original denominator. That can split up into three different pieces. I could have x minus 1, x minus 1 squared, x minus 1 cubed. So you basically do every power from the linear term all the way up to what you got. So like, let's say I had x minus 1 to the 7th. How many terms am I going to have? Potentially 7. To the first, to the second, to the third, to the fourth, all the way up to the 7th. Okay. Now, what goes on top? Well, what are each of the things inside the parentheses? They're all linear, right? What's 1 degree less than that? You only have to put constants on top, even though the second and the third one look like they're higher powers.
Can you use heaviside or no?
No, you can't use the heaviside trick with repeated roots.
Massive
Sorry.
bummer.
Yeah, massive bummer indeed. So the heaviside trick was sort of the cover-up trick that we talked about last time. That's the name attached to it. Sorry, can't do it. The heaviside trick only works if you have non-repeated linear factors only. If you have irreducible quadratics or repeated factors, it is off the table. Sorry. Okay. And you have to do it the long way then. Uh, sorry. Anyway. Okay. So what about the next one? Here you would have, oh, sorry, would help if I was competent this morning. Those are quadratics on the bottom. So why? Because what's on the bottom in each case? Right, it's an irreducible quadratic, and things that have irreducible quadratics get linear on top, 1 degree down. Okay, now so the way I like to think about this is you look at the degree of what's inside the parentheses, right? So the second term there is x squared plus 1 whole thing squared. What's inside the parentheses? And so that's why I put a linear on top. But it would never be that because a cubic can factor into a linear times an at worst irreducible quadratic, right? That's the whole point of the fundamental theorem of algebra. Right. So your numerators are only ever going to be constants or linears, never anything worse. And it's because when you factor your denominator, right, whatever polynomial that is, it can only factor into linear and irreducible quadratics at worst, right? If you have a cubic term, that means you're not finished factoring yet, okay? Now, in many cases, we'll actually give you the denominators pre-factored just for sake of time, but not always, of course, does that happen. Okay. Um, Gucci? Yeah. All right. So we're going to have to really blow through the next part. Let me actually, I want to start with a website. Um, so let me pull it up here. Um, oops. Damn it. Come on. Expand. Okay. There we go. Okay. Let me open this in this app. Hopefully it'll open the dang thing. Nope, it didn't. Okay, let's try that again. All right, where did it go? Okay, hang on a minute, guys. All right, we'll do it this way. Sorry. Where is the worksheets folder? There it is. Nope, not the text file. That's not what I want. I want the PDF. Oh, it doesn't. Okay, I'm sorry, guys. Let's just go through this, and we don't need to waste too much time. Okay, so great. Here's our what we want to consider. So, how did you guys do the warm-up problems? Well, one of them looked kind of like this, right? So, how do we do that limit? What's the trick?
Back to the top.
Yeah, in this case, we can factor, right, and then cancel out a term, and what normally looks like a problem, namely x being 3, becomes not a problem anymore, okay? Uh, so this limit is what we call indeterminate, because if I just plugged 3 into it, what would I get? I'd get 0 on the top. I'd also get 0 on the bottom. What is 0 divided by 0? It's worse than undefined. It's indeterminate. Okay, now what's the difference? Um, so pick a number from high school. Right. Okay, so pick a number. I can cut 4, 3, no, 4, 5, no, 3, so, right. So, the, it was another Monty Python joke. Yeah. Um, okay, so you picked the number 4. I can come up with a 0 over 0 situation where it ends up being 4. Okay, meaning that it's worse than undefined because it literally could end up to be any number. You just have no idea, or infinity. Who knows, right? So it's sort of the worst possible case that we can deal with. And so, yeah, this is a good way to think about it. Is 0 over 0 just means you're not finished. You got some other work to do, either factoring, some magic other algebra, or as we're going to learn today, this handy dandy trick called L'Hopital's rule. Okay. Now, if we want to learn about L'Hopital's rule, me being a historian, let's learn about L'Hopital's rule from L'Hopital. Okay. There's this one minor problem. It's in like French, oui. Okay. So Guillaume Le Marquis de L'Hopital was a pretty rich, I mean, he was a marquis, right? So he was rich. Um, and he basically, well, one of the things he did was uh, he wrote a calculus book called Analyse de l'infinité petit pour l'intelligence de la courbe, and I forget the rest of the title, but basically analysis of the infinitely small, right? So a calculus book, right? Uh, so he wrote an early calculus book. This dates to 1696, I think. And this his calculus book is the first time that the following technique appeared in print. And so it became known as L'Hopital's rule because it first appeared in L'Hopital's calculus book. He was not the person who came up with it, though. That was one of the Bernoullis. But he was a rich, well, okay, so this happens all the time in mathematics where things get named after the person who didn't discover them, right? So things get misnamed all the time, especially when you look back historically. Okay, so um, what what he's doing here is basically talking about the problem of 0 over 0. Okay, so where can we see that? Well, this would be in this opening statement. He says, "Dont les numérateurs et les dénominateurs deviennent chacun 0 lorsque x equals a." Okay, so they both become 0 when x becomes a. Okay, which is sort of an old style way of saying as x approaches a, this is of the form 0 over 0. Okay, and so then the question is, what do you do? Um, okay, so what he does, he goes through sort of an abstract proof here, but then let's go to the next page because that's where he has two examples. Okay, we're actually going to look at the second example first because it's slightly simpler. Okay, all right, so soit y equals, or y égale, AA minus AX over A minus the square root of AX. On trouve y equals 2A lorsque x equals A. Okay, so what he's saying is that we're going to show that if the limit of that thing as x approaches a comes out to be the value 2a. Okay, and we'll go through the derivation of that in a minute. Okay, so anyway, me being a historian type and this being a liberal arts college, I really want to um, make sure that we get a little bit of history. And okay, you don't have to read French to appreciate this, but here it is. Okay. Okay, so let's go back to, I just want my, um, let's see. Of course, it's being annoying. Oh, here it is. No, but that's the LaTeX version. Okay. Forget you. I'm just going to go to here and just write it. Okay, so what L'Hopital's rule says, suppose that you've got a limit as x approaches a, and by the way, a could be infinity or minus infinity, that's all right, of a fraction of two functions, right? So there's something on the top, I'll call that f, there's something on the bottom, I'll call it g, great. And it's of the form 0 over 0 or infinity over infinity, okay, one of the two, okay? Then the limit as x goes to a of f of x over g of x, so this is the original problem we cared about, is equal to the following. It's equal to the ratio of the derivatives. Okay, so let's make sure that we're clear what the statement is. Any questions on just the statement of what L'Hopital's rule is? Are we okay with that? After you guys scribble it down. Okay, looking at the statement of it, let's maybe think for a minute, do some metacognition. Why is it that we don't talk about L'Hopital's rule until Calc 2 instead of, we could have done this in Calc 1. In fact, how many of you guys learned L'Hopital's rule in high school or saw it? You did? Okay. In Calc 1, right? So why is it that it's maybe a good idea to not talk about it until Calc 2? Well, yeah. Okay, here's one reason I like to think of. When you guys first learned the quotient rule, what was the biggest mistake you guys would make? Was to say the derivative of a fraction is the fraction of the derivatives, right? And we'd beat you with the stick and say, no, no, you have to use the quotient rule. And eventually it sunk in, right? Well, look what I'm now telling you to do. I'm telling you to take the derivative of the top and divide it by the derivative of the bottom. I am not saying to compute the derivative of the fraction f over g. I'm saying just take whatever the derivative of the top is, whatever the derivative of the bottom is, and form that ratio of the two things. Okay, but this looks like the wrong version of the quotient rule, that sort of mistake version of the quotient rule from Calc 1. So, we spend weeks and weeks beating it into Calc 1 students' heads to not do this, and then we turn around and say, oh, by the way, do this. Okay, so now, yes, they're two different situations, but that can be confusing to students. That was true. You're not done. L'Hopital's rule is just another trick in your bag of tricks for how to deal with said situation. Okay. Um, okay. So that's the rule. Let's apply this and let's actually do L'Hopital's first example. Um, okay, my computer is getting ready to die because it is not charging, and it is not charging because this outlet is, okay, we may have a problem here in a moment. Why are we not charging? Hang on, guys. Let me resolve this crisis before we move on, because otherwise the whole show is going to come to a halt. Pardon my reach under here. There should be a sorry, I'm literally under a table right now plugging in a cable. Nope, that didn't work. Okay, so why is this not charging? Well, it's heating up like it's charging. Yeah, I may have to switch to a different cable. I hope something didn't break with this one. Okay, I'm really sorry about this, guys. Let's try a different one. It's a good thing today's Friday because today has not been going so great. Okay, kapla. So there must just be something wrong with that cable. All right, disaster averted, guys. Okay, so let's look at L'Hopital's example. So let me go back to the website and let's look at how he states it. Um, the second one. Okay, so it's a little hard to read, so let me blow this up a little bit. Oops, there. Okay, I know that's a little blurry, but it's AA minus AX over A minus the square root of AX. Okay, so let me write that. So we're basically considering this problem. Okay, now the first question is what the heck does AA mean? Any ideas? It's just A squared. It's an old style of writing. Um, yeah, I know it's that easy, right? Um, that's all it means. Okay. So in older text, up until I don't know if there's a firm cutoff date for it, but it's quite common in sort of 17th, 18th, 19th century that instead of x squared, you would see xx. Um, However, most of the time, x cubed would be x cubed, not xxx. Okay, or something like that, right? So it was and in some authors, it's actually sometimes you see x squared and other times you see xx. So it's just it was not a consistent notation. Okay, if I plug a into the top and the bottom here, what do I get if I plug a into the top? Get a squared minus a squared, which is clearly zero, right? And then on the bottom, I would get a minus the square root of a squared, which is also zero, right? Okay, so this limit is of the form 0 over 0, which means L'Hopital's rule applies. And what does L'Hopital's rule say to do? Take the derivative of the top and the derivative of the bottom and form the ratio. So what's the derivative of the top? Okay, good. Sorry, let me be more clear. What's the variable here? X. A is a constant. Okay, so when I say the derivative, I mean with respect to x. So what's the derivative of a squared? Cole.
A squared.
Uh-huh. If x is the variable and a is a constant, what's the derivative of a squared?
Two.
A zero. It's a constant, right? Yeah, okay, so yeah, that's a trap. So no, fair point, right? When I do this, what is the variable? It's x, and the reason is because x is approaching whatever, right? A is I'm thinking of here as a constant. Okay, so the derivative of the top is just minus a, right? That's it. Um, yeah. Okay, what about the bottom? That's a little bit worse because we got the square root. Well, the a term would go to 0, right? And so what I want to do is I want to think of root ax as being ax to the minus or to the 1/2. And so the derivative of that would be this by the chain rule, okay? Um, and so then what do I have? I'll have 1/2, what did we say? Ax to the minus 1/2 times a because of the chain rule. What happens to the two a's there? Yeah, this cancels with that. And I have a negative exponent, so couldn't I write it like this? I'll put a 2 here, and I'll put the square root of ax there. Negative, yes, thank you. Um, yeah, okay. All right, so we're good. Can I just substitute x equals a in at this point? I can totally do that, right? Am I going to end up with any uh, square roots of negatives or 0/0 or anything like that? Nope, no problem. Just plug it on in. Okay, so what I get is what? It'd be negative a over 2 would be the limit. Is that what L'Hopital said it should be? Or did I screw something up? Right, right. Okay. Technically, it'd be absolute value of a, but his assumption here is that a is positive, so it's not really a big deal. Okay, is that what L'Hopital had said? He said 2a. Oh, I'm sorry. I know why. I I botched this. Okay, this is actually a problem when you're reading historical sources. Let's look very careful at the form that he wrote it in. What was the how did I interpret that? Well, sorry, the denominator. Okay, is the x inside or outside of the square root? Okay, I think actually he's interpreting it as outside. Okay, which means we basically did the wrong problem.
I think you were right. I think you just divided by 1/2, and then you just put the 2 in the denominator instead of putting it up here.
Okay. Oh, yeah, I'm sorry. No, we were right. Yeah, thank you, Donovan. Let's go back to the sheet here. Um, where was the error? Here to here, because 10 out of 7 Americans struggle with fractions. Okay, so that should have been 1/2, which means that this would be minus 2a. Okay, so that fixes that problem. Where's the problem of, oh, here, okay, I see the other issue. I should have had a minus right here, right? And then this minus and this minus um, should have been that. Okay, so we did interpret him correctly. I'm just incompetent. Sorry. Yeah, I know. Even math professors. Okay, so let's be clear. What did I screw up here? I forgot a negative, and I also can't work with fractions because I'm a moron, right? I did. My 32-bit brain could not compute. Okay, so I forgot the minus that went in the denominator because of I just did the derivative of a negative quantity. Okay, so that red minus sign, I forgot. The red minus sign cancels with the minus sign in the numerator. Okay, so that fixes why we had our answer should come out to be positive. And then the other error was the 1/2 in the denominator. Well, dividing by half is really multiplying by 2, not dividing by 2. Okay, so fix that, and so we end up with getting 2a as our answer. Okay, which is what L'Hopital said it would be. Okay, good. That's not too horrible, is it? No? Yeah, okay. So let's actually go back just one moment, because this will make for a good exercise, is to do L'Hopital's second example, okay, which is a little more complicated and a lot harder to read. I'll type it out for you guys, um, because it's got cube roots and stuff, and just to make sure that we actually do the correct problem. It works out a little bit nastier, but eventually you end up, it's fine, okay? Um, and actually, what's interesting here is you actually see not just the answer, but his solution to it. Um, yeah, so anyway. Um, and what you end up getting there is 16/9 A is the particular limit. Okay, great. Okay, so I have really blown through my time today, which is unfortunate. Let me go back to the sheet, just for, okay, where did I put it? Here it is. Let me go back and back to my sheet, because there's a lot of situations that we haven't talked about here. Um, in particular, sometimes you have to use L'Hopital's rule more than once. Okay, so for example, on number 4 there, is it infinity over infinity? Yes. If I take the derivative of the top, I'm going to get 2x plus 1. If I do the derivative of the bottom, I'll get 3x squared plus 2x plus 1. Well, if I let x equal infinity, it's still infinity over infinity. So just do it again. Okay, so like integration by parts, sometimes the solution is just to do it a couple more times, and eventually it works out. Okay, I'll talk about my Admiral Akbar example next time. The other thing is that for 6 and 7, sometimes you have to do a little bit of algebraic prep work before you can use L'Hopital's rule. Because, for example, if I let x equals infinity in number 6, what do I have? I have infinity times e to the minus infinity. What's e to the minus infinity, basically? That'd be like 1 over e to the infinity. Well, e to the infinity is going to be gigantic, infinity, and 1 over an infinite quantity is 0. Okay, so this limit is of the form infinity times 0. Is that 0 over 0 or infinity over infinity? No, it is not. Okay, but with some algebraic work, I could rewrite it in that form. The solution for this one is, what does e to the minus x really mean? Right, so I could rewrite number 6 as x over e to the x, and now it is in a form that L'Hopital's rule applies. Similar thing is going to happen in number 7, but in number 7 we'll have to use a logarithm. Okay, so I've kind of blown through my time here, and I'm sorry about that. Uh, so if I could get you guys to, there are examples that look like number 6 and number 7 in the section of the book. Take a look at those, and if you've got questions, we can talk about that, I guess, what, Wednesday next week? Or maybe we'll have a little bit of time Monday. But excuse me, Monday, what are we doing? Yes, yes, your next fluency assessment, which will have on it any standards that you have not yet demonstrated mastery in. Okay, so in particular, it'll have the new ones, meaning like the techniques of integration standards, because well, we haven't examined you on those yet. So that stuff will be new, and it's okay if you don't finish all of them, right? So I would rather you do half the problems and just do them flawlessly than half-ass all of them, right? Okay, so because if you don't demonstrate mastery on Monday, no problem. Just, you know, I mean, not kind of kick the can down the road. Those of you who are online, I will send you instructions for how to deal with that this weekend, and then you'll be ready for it Monday. Okay, we better quit here because it's 55 after. And so, yeah, just to recap, please have a look at some of the more exotic examples in section 6.7. We skipped 6.6, which was on hyperbolic functions. We may come back to that later. So just have a peek at some of those examples, and then we can talk more later. All right, let's see if this fancy thing works. Nope, didn't look like it worked. Nope, okay. All right, see you guys later.